energy hydraulic or pneumatic dampers. In most shock absorbing system, we need oil or some other means to absorb energy. So the main intention is to prevent unnecessary shock transmission from one component of the structure to another. We provide some kind of damping system. So how that damping system affects the total vibration. So that is what we are going to see. Okay. So for that, we need to know the the amount of energy dissipated due to damping. That, as we know, energy is force times velocity. So, which is force is just c times dx dt square, means the second means c x dot square. Okay, so this is the energy due to the damping, and this energy due to damping is with negative sign, which indicates the energy dissipation. The negative sign indicates the energy dissipation. So how we can derive that the amount of energy dissipation? So dW is equals to minus C dx dt. Dx dt means the first derivative of displacement, that is x dot square dt. That means the equation x is equals to x sine omega dt is the solution for the given vibration. So simple harmonic solution. This is but with the damped frequency. Okay, here it is sine omega dt means damped frequency with respect to time. So this is the meaning of. Now integrating this expression, what we can get is for one complete cycle of vibration. Complete cycle means hysteretic cycle. The cycle starts from 0 to some time period t. That time period for damped system is 2 pi over omega d. Omega d is the damped natural frequency. Okay, so that is one complete cycle. The time taken to complete one damped frequency. So for that, we integrate the whole system and we change the time domain of analysis to the frequency domain. This omega dt is the frequency domain analysis. So it is changed to this, and then finally we get the amount of energy absorbed or the amount of energy dissipated due to the damping. So which gives us pi c. C is the damping ratio or the damping coefficient, not ratio but coefficient. Omega d is the damped natural frequency, and x is the maximum amplitude of vibration. So finally we can get delta w, that is 0 to t d, integral of 0 to t dw gives us change in w. So that change in w is equals to pi c omega d x square. So this is the amount of energy dissipated during one complete cycle. And the cycle for structural purposes is known as hysteretic cycle. This cycle is called hysteresis cycle. So each of the components of this hysteresis cycle for minus x to plus x, that means the amplitude of vibration for minus x to plus x within that boundary is given with this hysteretic loop. This loop is called hysteresis loop. So this is a single degree of freedom with damper and what we call stiffener. This K is stiffener and the C is the damper. So this is what we call hysteresis. So this shows that the energy dissipated delta W is proportional to the square of the amplitude of the motion. So the amplitude of the motion affects in the square mass, okay? So note that it is not a constant for given values of damping and amplitude, since delta W is as a function of the damping frequency omega d. So it is not natural frequency, but damped frequency. So we tried to answer this question in last class, that does a spring force will do any network over a complete cycle? The answer is not. To prove that, how we calculated it, we assumed x of t is equals to x sine omega dt as a solution for f is equals to minus cx kx. This is the force. The force which is equals to minus c times x dot. This is due to the damped vibration. Kx is due to the material stiffness, so that f is equals to, just assuming x is equal to x sine omega dt, and x dot becomes omega d x cos omega dt. So substituting these values into this equation, we can get the equation of force. And now substituting this equation of force into the delta W, means this delta W is Fx dt. It is force times velocity. So just substituting this value, finally we can get only c pi omega dx square. But the component of k omega d x square part becomes 0. If you substitute 0 for this one, cos 0 is 1. Again, if substitute 2 pi omega d instead of t here, this also gives you 1. So 1 minus 1, it is 0. So the k component becomes 0, but the c component having c pi omega d x square. So that the spring constant will not have any effect in the damping. But the only component which take care of the system, or which saves the system from unnecessary kind of impact, is the damping part. So this is what we have concluded in the last class. Okay. Now the fraction of the total energy. Fraction of the total energy in each cycle of motion becomes what? We can observe the fraction which is delta W over W. So for that, the total energy of the system is considered W, which can be expressed either in the maximum potential energy, half kx square, or maximum kinetic energy, half mv square, or which is equal to half m omega d square x. This v max is equals to omega square d x square. So substituting this thing, we can change the ratio or the fraction of total energy to dissipated energy. This is dissipated energy, this is total energy. So dissipated energy is pi c w dx square, as we have derived in the previous section. And the total energy is the kinetic energy, that is half mv square, or which is half mwd square x square. So by doing that, finally what we can get is 2 pi c over md is the ratio of the delta W to W. So that delta W to W is also again rearranged with the help of damping ratio. Okay. So the damping C over 2m is zeta, as we know. That is delta actually. So that finally what we can get is 2 times delta, or approximately 4 times pi zeta. That is another relation with various constants. So the equation delta W over W is called the specific damping capacity. Okay, and is useful in comparing the damping capacity of engineering material. So various engineering materials have various specific damping capacity. So whenever we are selecting material, we have to select a material with an appropriate damping capacity or specific damping capacity. Another quantity is as the loss coefficient is also used for comparing the damping capacity of engineering material. So the loss coefficient is given with delta W over 2 pi W. Okay, that is 2 pi, 1 over 2 pi is of the one cycle condition, so that which related is delta over pi, and which is approximately equal to 2 times zeta with the damping ratio. Okay, so by such kind of analysis, we can select an appropriate engineering material. Okay, so free by now, let's see the Coulomb damping. This Coulomb damping is directly related with the friction, the surface friction, or the friction coefficient. In your statics and dynamics course, you know what is the dynamic friction, what is the static friction. So here what we are understanding is the static friction, or friction of the free surface. Okay, whenever, look, this is the mass, this is the damper, and this is the stiffener. So whenever this mass tends to move in this rough surface, the surface try to deny the motion of the mass. So that is related with friction surface. Will produce frictional force in the opposite direction to the motion. Okay, that force is, the friction force is equals to mu times n. N is the normal force. Weight is the due to the gravitational effect, weight is there. So when this mass tends to move to the right, and this friction will deny to the left. Okay, so mu n is the friction force. So then after, if the mass is tend to move to the left direction, then the deny will position. So this free body diagram illustrates those conditions. Okay, so free vibration with dry friction, or dry friction means this Coulomb damping is kind of dry friction. Okay, in vibrating structure, whenever the component is slide relative to each other, dry friction damping will appear. Okay, as stated, Coulomb damping arises when the body slides on the dry surface. So Coulomb law of dry friction will works here. Its size, force of friction is equal to mu times n, and n is the normal to the surface. So the normal and the weight in the vertical direction is, normal is equals to weight, so that mu times W or mu times mg. So mu is the friction coefficient. Okay, so we can express the friction or the dry friction or Coulomb friction in this manner. How we can relate it to our equation? እየተከታተላችሁኝ ነው? ሜቢ ኢንተርኔት እንትን ሊኖር ይችላል፣ እሱን እየተቋቋማችሁ
ይሰማ።
So Coulomb damping is sometimes called constant damping, since the damping force is independent friction coefficient mu. Okay, so we have two cases. One of the cases when the object is moving to the right, or the second case is when the object is moving to the left. Okay, so let's consider the first case as when the object is moving to the right. Okay, when x is positive means the movement in the forward direction, and dx dt is positive, or when x is negative, dx dt is positive, means the rate of change of displacement is positive. For such case, we have from mass, the Newton second law, we have this relation, mx dot dot, or mass times acceleration, is equals to minus kx minus mu n. Okay, this is one of the relation, which is equals to mx dot dot plus kx is equals to minus mu n. So this partial differential, this differential equation, it is not partial but ordinary differential equation of the second order. And it is not homogeneous equation. This equation is non-homogeneous. The previous case mx dot plus kx is equals to 0 is the homogeneous equation, but this one is non-homogeneous. Okay, so the solution for such kind of non-homogeneous equation from your linear algebra is x of t is equals to a1 cos omega nt plus a2 sin omega nt minus mu n over k. This is the type of solution for the non-homogeneous second order equation. So this A1 and the A2 are amplitude constants, which should be determined from some prescribed condition. This mu n over k is this representation, or the contribution of normal force at the frictional surface. Okay, so now let's consider omega n is equal to radical of k over m, which is the frequency of vibration, and A1 and A2 are constants, which are amplitude constants, whose values depends on the initial conditions of the this half cycle. Now what we are considering is only half cycle. Why? Because our mass move in the forward half cycle and comes back to its initial equilibrium position in half cycle. We are not considering from negative to positive cycle here. Okay, so our consideration is for the half cycle vibration. So that is the first case. Look, this is solution for this mx dot plus kx, which is equals to minus of mu n. Again, the second case, when the mass is vibrating to x is in the positive direction and the dx dt, that means velocity in the negative direction, or dx dt is negative for the next half cycle. This is for the next half cycle, to the right to left motion, because the motion of this block initially from here to here, that is case here, case B. During this time, the mass is moving forward in this direction. But in the second case, the mass is moving to this direction. So the opposite direction is this. Friction is acting in the opposite direction, this indicates. So what we have case 2 is this one. Okay. This is case 2. So during case 2, the equation of motion is mx is equals to minus of kx plus mu n, which is mx dot plus kx, which is equal to positive mu n. Now the solution is also here, a3 cos omega nt plus a4 sin omega nt plus mu n over k. So these four equations are very important, and we have to synchronize the four equations together. So you can see the vibration condition due to Coulomb damping. Okay, it will go to some maximum, it will decrease, and finally goes to some kind of infinity. So Serrano, Srak aለ አዎ ስራክ እየሰራ ነው። ውሰዱ ከሱ ጨርስ ብያለሁ። Okay, sorry for the disturbance. Anyways, the term mu n over k, which is appearing in equation, is constant. Mu n over k, this is constant term. N is the normal force, mu is the frictional coefficient, k is the stiffness of material. So this term is constant in the first equation, also in the second equation. Okay, so the virtual displacement of the spring under force mu n, if we're applied as a static force, then we can obtain this kind of vibration. So the initial amplitude x naught is here. And then this amplitude goes to some to the negative direction, minus x naught minus 2 mu n over k. So this minus indicates the location in the downward direction. And the amount of decrease in amplitude within this half cycle is mu n over k. This range, mu n over k, is the amount of amplitude decrease. Again, in the second half, similar condition will happen. This is for pi over omega n time. This is actually time domain t. So the time t is equals to pi over omega n. Again, for the next pi over omega n, we have also similar decrement, mu n over k, so that it is totally from here to here, it is minus 2 mu n over k decrement, okay, from x naught, because from here to here it was x naught. Now from here to here it is x naught minus 2 mu n over k, mu n over k plus mu n over k from this direction. So it is decreased. Again, the next half cycle, it decreases in similar way. Okay, it decreases again x naught minus 4 mu n over k. 4 means 2 plus 2. Okay, here there is a decrement of mu n over k. Here there is a decrement of mu n over k. So there are 1, 2, 3, and 4. So that it is about 4 mu n over k decrement. So this is not kind of logarithmic decrement. In the previous case, in the free vibration condition, what we have observed is a logarithmic decrement. But here, it is not like that. This is just a constant decrement. At every 1/4 of cycle, there is mu n over k decrement in the amplitude. Okay, in one complete cycle, there is 4 mu n over k decrement in the amplitude. So that is what we call Coulomb damping condition. So how we can synchronize the equations? Okay, the equations, there is maybe this may be new for you. The Signian function is new for you. Because this is not such familiar mathematics, but we can express the equation in Signian function. So Signian of x dot implies 1 if f1 f4 or for x dot greater than 1. For the positive x dot, for the positive velocity, it is 1. It is 0 for x dot is equal to 0. And it is minus 1 for all x dot less than 1. Okay, for negative velocity component, it is minus 1. For positive velocity component, it is 1. So it is in between 1, 0, and minus 1. So we express the total equation in terms of mx dot plus mu mg. This mg is the weight. Okay, that means mg sine x signum of x dot. This mg is just the weight of, or it is the normal force. You can represent this mg by n, or you can represent this mg by w. Okay, so it is mx dot dot mu times w signum of x dot plus kx. So this equation synchronize the equation number 1 and equation number 3. Equation number 1 means mx dot dot plus kx is equal to minus of mu n. And third equation is mx dot dot plus kx, which is equals to mu n. So these two equations are together expressed in a single equation by using the Signian function. Okay, so this is the function which relates such kind of two various situations. Okay, so to find the solution using this procedure, let's condition some initial. Let's consider some initial conditions. So the initial conditions, x of t at time t is equal to 0 is equal to x naught. Assume this is assumption actually. Sometimes we may have velocity and maybe displacement is 0. Now let's consider velocity is 0 at time t is equal to 0 and x of t is equal to 0 at x naught, because as you see here, initially at 0 time there is x naught. Okay, so at this moment velocity is 0 and then displacement is x naught at time t is equals to 0. So considering that condition, x of 0 is equal to x naught, then it gives us a3 plus mu n over k. Then a3 is equals to x naught minus mu n over k. So a3 is this value. Now we are just finding the constants a1, a2, a3, a4. Again, using equation number 4 and substituting this condition, and x dot is 0, so we can find a4 is equals to 0. Okay, x dot means minus a3 omega n sine omega n t plus a4 omega n cos omega n t. It is just derivative of this equation. If you derive this, the first derivative of this equation gives you a3 minus of a3 omega n t cos sine omega n t plus a4 sine a4 omega n times cos omega n t. And this is constant, so that will be 0. So by doing that, we can find this equation, and the x dot of 0 gives us a4 is equal to 0. So our equation is now coming to the solution for this equation becomes x of t is equal to x naught minus mu n over k the whole times cos omega n t plus mu n over k, because by substituting a3 in the place of in equation number 3. Let me show you equation number 3. Substitute a3 here. a4 is 0. This component is 0. a3 is x naught minus mu n over k, so that we substitute this value here, then plus mu n over k. So this is solution for the second condition. Now the solutions become this one, that is we already obtained this solution. This solution is valid for half cycle only. As we have discussed, in every cycle we have such kind of solutions. So this solution works for 0 to pi over omega n. Okay, 0 for the time 0 less than or equal to t less than or equal to pi over omega n. That means, look, 0 is here, pi over omega n is here. This is the first half cycle. Okay, for the first half cycle, the amplitude, which this is K3, no, A3 in our case. This is for the first condition. So, so we have, and when t is equals to pi over omega n, the mass will be at its extreme left position. The mass displaced from its equilibrium position to extreme left position. Okay, and its displacement from the equilibrium position can be found as minus of x1. Means it goes minus x1 plus x1 like that. So minus of x1 is equals to x of t is equals to pi over omega n. Initially, x of t is equals to 0 condition is satisfied in this equation number 6. Now the next condition is minus of x1 which is equal to x of t is equals to pi over omega n. So that means x naught minus mu n k cos pi, which is equals to minus of x naught minus 2 mu n over k. So since the motion started with displacement of half cycle, the value of x becomes minus of x naught minus mu n k. Minus means in the downward position. This minus, especially this minus, indicates the position in the downward direction. And for the time t pi over omega n is mu n over k. So that we already discussed. So this is question number 6 already stated there. And then x dot of equation number 6, just derivating this one, what we can get is omega n times x naught minus mu n over k sine omega n. Again, using this equation, we can apply and find a1 and a2. Now, in this case, a1 is found as x naught minus 3 mu n over k, and a2 is 0.
ከአንድ ደቂቃ በታች ነው ያለው። ከአንድ ደቂቃ በታች ነው ያለው።
ኦኬ ኦኬ። ሶ እንደገና እንገባለን፣ ተመልሰን ጆይን እናደርጋለን፣ ሰዓቱም ይሄዳል። እሺ። So this is generally the representation. General representation or the general solution becomes x of t is equal to x naught minus 3 mu n over k cos omega n t minus mu n over k. So this is for valid only for pi over omega n. Pi over omega n is this position. 2 pi over omega n. 2 pi over omega n is. So now it is full complete cycle. What we have discussed is